Hi class, 8.7 is next. This is the last unit from chapter 8 and the last section before our next exam. Product to sum identities. There's 3 identities here in the box that prove useful from time to time. These are not amongst the identities I'm going to ask you to memorize though, but you could be responsible for knowing how to create them using previous identities. For example, I'm going to create the first identity you see here, so this one right here. And I'm going to do it using the sum and difference identities for cosine. The reason I know to use these two is because those two are present in the identity. If I was trying to show this middle identity, then I would start with these two again. And if I was trying to create this last identity, I would start with sine difference and sine sum identities to begin with. So you can prove all 3 of these identities that are in this box in a way that's similar to the way I'm going to prove the first one. Okay. So the cosine of alpha plus beta is equal to the cosine of alpha cosine beta minus sine of alpha sine beta. And the only difference is when I make the subtraction is that this difference goes to addition. Now look at the operation that is right here, minus. I'm going to essentially mimic this structure. I'm going to make the, well, I'm just going to write this out. Let's just write this out and see what happens. So we have cosine of alpha minus beta minus the cosine of alpha plus beta. Okay, then I'm going to replace the cosine of alpha minus beta with cosine of alpha cosine beta plus sine alpha sine beta, and then subtract, and then have to use parentheses here. Now I'm going to replace this one here with its identity, which is cosine of alpha cosine of beta minus sine of alpha sine of beta. Okay, and what we wind up getting is distribute the negative. You're going to see that after I distribute the negative, that this term and this term are going to cancel each other, but this term and this term are going to add to each other and become double. So we wind up getting 2 sine alpha sine beta. Now follow the chain of equal signs. Right, this statement is equal to this statement. Now just divide both sides by 2, and you wind up producing this statement. And as I said, it's a similar process. Just start with the structure you see in the brackets, use the appropriate sum or difference identity, and then ultimately solve for these parts, and you should wind up producing these identities. Then there's sum to product identities. Sine of alpha plus sine of beta is equal to, etc. There's a whole bunch here. I'm not going to read them all. These sometimes are useful as well as we move forward in mathematics, but we're just going to use a previous identity to create the first identity we see above. Okay, what I'm going to do is I'm going to start with this identity we have right here, which is an identity that was from up here, a product to sum identity. And I'm going to replace the u and the v with these expressions respectively so that I can mimic the structure sine u cosine v. Okay, so this winds up being, right, I want to change the u to this. So we get 1 alpha plus beta over 2. And replace the v in the statement with alpha minus beta over 2. Okay, I'm going to do the exact same thing on this side. The u gets replaced with alpha plus beta over 2, and the v gets replaced with alpha minus beta over 2. The u gets replaced with alpha plus beta all over 2, plus, and then the v gets replaced with alpha minus beta all over 2. All right, now simplify what's inside these brackets. This negative is going to have to distribute. We have a common denominator of 2 already. So we wind up really getting alpha plus beta minus alpha plus beta all over 2 inside there, once I distribute the negative and combine with a common denominator. Plus, over here I don't have to worry about distributing a negative. So this will just be alpha plus beta plus alpha minus beta all over 2. And then simplify what's inside these parentheses. And notice we get the alphas will cancel, right? And the alphas are gone. The betas will add together, become 2 beta, but then divided by 2, it just goes back down to beta. Whereas over here, in the second one here, it's the betas that cancel, but the alphas combine to be 2 alpha, and then divide that by 2 just gives you just alpha. Okay, now keep in mind that we're saying that this is ultimately equal to this. Now I just have to double both sides to move this 1/2, double both sides, and you wind up producing our first identity that's up here. Let's zoom out so you can see all of it. Double both sides and you will produce this first identity. That's the only one I'm going to demonstrate. The others I'll leave to you to figure out on your own. And then we just have one last slide for Chapter 8. Using trig identities and solving trig equations. Use trig identities and the unit circle to solve the following trig equation. Confirm your answer using technology. All right, here we go. When you have a trig equation where the arguments don't match, then this is problematic. Your first goal, by arguments I mean the 2u and the u. We want these to get to the point where they're referring to the same u, the same angle. Not one is double the other. So I want to use an identity that will go from a 2u to a u. Well, the one I'm going to use for that was the double angle identity for sine. Let's back all the way up. Back up to double angle identity for sine. Here it is. The sine of 2 of anything is equal to 2 sine thing cosine thing. Right? These don't have to be thetas. This could be an x and these would be x's. Right? This could be u and these would be u's, etc. But we're going to use that identity on this very last problem. Here we go. So according to that identity, the sine of double an angle is twice the sine of that angle times the cosine of that angle. So we wind up producing this statement. Now right here, so far we've accomplished our goal of getting all the arguments down to the same angle. They're all u now. Now we can start thinking about some of the strategies that we did earlier when we learned how to solve trig equations. It's very tempting for people to now divide both sides by cosine of, cancel that, But this is a bad thing when you do this because you lose answers. We've had this conversation in the past. Like if you have x squared is equal to x and you divide both sides by x and you say 1 is an answer, but you just lost the answer 0. Right? You would get that answer if instead of dividing by x, you subtracted the x over and then factored, and then you get your multiple answers, right? 0 from here, 1 from here. So we want to be careful here with trig as well. Don't divide away the cosines. Instead, subtract a cosine over and then factor. So subtract cosine over and then factor. I'm going to factor out that cosine. All right, this says to use the unit circle as well. I'm going to bring in the unit circle, actually. I don't know why I didn't do this earlier, but let's bring this unit circle in. Let me crop it slightly so we don't have these black boundaries. A little bit more cropping on this side. Good enough. All right, so we have this to refer to. Oops, our unit circle. Let me shrink it a little bit. Having a hard time selecting it and oh, I have to do it this way. Okay, there we go. There's our unit circle. We'll be looking at that in a moment. Okay, this is all equal to 0. And now we can set these factors equal to 0 separately. And we get some answers. Keep in mind that we only want u's between 0 and 2 pi, so we want a full rotation's worth of u's. And we want to identify all angles where the cosine is equal to 0. So we look over at the unit circle and we say, okay, where is the cosine 0? Cosine is the first coordinate that's going to happen up here and down here. So we have two different angles, 90 degrees and 270 degrees. And we can do this in, let's give answers in radians this time. So the first equation gives us the answers. U could be 90 degrees, which is pi halves radians, or U could be 270 degrees, which was 3 pi halves radians. Now let's focus on this equation. Solve for sine u. So we have 2 sine u is equal to, right, add the 1 to the other side, now divide by 2. And we're left with this. We want to find all angles now from 0 to 360, right, on this interval, where the sine is 1/2. Well, the sine is the second coordinate, and the second coordinate is only going to be positive in the top half of the circle, and it's positive 1/2 here and here. So our angles are pi 6 and 5 pi 6 are the two angles. So you can be pi 6 radians, or you could be 5 pi 6 radians. All right, and these are all the answers, which we're going to confirm with technology here. But let me go ahead and put all my answers together. And I'll put them in order. There's a total of 4 of them. The lowest was pi 6. After that was the pi halves. After that was the 5 pi 6. And then the final largest of my answers was the 3 pi halves. To confirm this with technology, I'm going to graph this equation and graph this equation and look only on this interval and look for points of intersection. Let's go to Desmos. I think I had some stuff here from before. Let me have to delete all this. Oh no, it's all gone. Okay, so I'm going to graph y equals the sine of 2x. I'm using x instead of u, so it graphs. And the other side of the equation was just cosine. So y equals cosine of x. And I'm only interested between 0 and 2 pi. So let's go to my wrench and let's do step size of pi. And we're only interested in intersections between 0 and 2 pi. So looking only on this window right here. Click on either one of these and then find points of intersection. Those are the only points of intersection between the two curves, between 0 and 2 pi anyway. And notice the x-coordinates of them. Those are the solutions we got in the same order. Pi 6, pi halves, 5 pi 6, and then 3 pi halves. 4 locations between 0 and 2 pi where these two curves intersect. Okay, that wraps up Chapter 8. And between Chapter 8 and Chapter 9, we will be having a test. Stay tuned for all of those details.